Every millennium. Tesla certainly qualifies as one of them. Now, presidents of the IEEE, this guy, Buck, is a very interesting character. This is the work of Nikola Tesla, and his great conception of the rotary field seems to me to be one of the greatest feats of imagination which has ever been attained by the human mind. Alex Anderson, who worked at GE, helped to generate high-power RF generators, that in almost every step of progress in electrical power engineering, as well as radio, we can trace the spark of thought back to Nikola Tesla. Tesla did it first. Got the idea and just said, oh, this is an interesting thing, and threw it aside, went on to the next one. I can't find any mistakes in Tesla's thoughts. By the way, this is in a letter that you can find up there at Niagara Falls. If you go there and you go to the museum, it's up there. Levy Forrest, who invented the triode, said, if I could be any other man, I'd be Nikola Tesla. All right? There's one I want to call your attention to, Bernard Behrend. Behrend is the first guy to really write a book about how generators work. I'll save that till later because we'll come back to Behrend. Jonathan Zenneck is an important character. He's the first guy that writes a radio engineering handbook. It's published in 1915 by McGraw-Hill. And Zenneck was a student of Arnold Sommerfeld at Munich, and later on he becomes the chairman of the physics department there. By the way, Sommerfeld, you all know Sommerfeld, with all of the Nobel Prize winners, the students all got Nobel Prize. If you didn't get it, the students all got it. He wrote a letter to Tesla and said, he said, well, the lectures, he read, you can get Tesla's lectures today. If you go to Barnes & Noble, they got, it's a big, thick book for $8. You can get all these lectures that are delivered, I think, up until about 1894 or so, just before the fire. He said those lectures opened a new physical world to me. He was one of the kindest men I've ever encountered. The hours which I was permitted to spend together with him will always be among the fondest memories of my life. By the way, Zenneck was also vice president of the IRA during the 1930s, okay, just before World War II. Who are his other friends? Crookes, Sir William Crookes, was a very close friend of his. In fact, there's a famous picture of Tesla sitting in front of museum with his sparks and so forth. And written in his own bold hand writing, he says, to my dear friend, Sir William Crookes, whose letters I always read but never respond to, or something like that. Lord Rayleigh, Dewar, von Helmholtz, and just these people who we think of as great scientists held Tesla in extremely high esteem. By the way, Tesla's grandnephew is still alive. His name is Bill Turbo. He's a graduate of Purdue in the mechanical engineering department. And he has many, many stories to tell about, and personal stories of his experiences with Tesla. The image of Tesla that appears to us, that emerges in all of this, don't read what people wrote about Tesla. Throw all those books that people have been writing the last 50 years away. Read what Tesla wrote himself, right? But the image that emerges is a happy, joyful, gracious, charming, winning smile, and firm handshake. They always tell you about this, right? He's afraid of microbes. He wouldn't shake hands with people. That's pure bunk. Yeah, he had a firm handshake is the description that. What's the guy that wrote that? It used to be Radio and TV World back in the 50s. Why can't I think of his name? The editor of that, Hugo Gernsback, wrote, described how Tesla's handshake was. He was so firm he couldn't understand. He was a cosmopolitan New Yorker in speech, manner, demeanor, and we see him as one of the happiest men on earth. He wasn't a mystic, and he didn't perform his research in a vacuum. But what he did was just so astonishing. And that, I think, is what we would you have been delighted to have been able to spend your life doing the kind of work that he was doing? One other thing here, before we get into some technical things. This is a quote by Alexanderson. When he was president of the IRE, Alexanderson was at General Electric, which was a competitor of Westinghouse. Tesla's patents were all, power patents were all purchased by Westinghouse. And let's see, my recollection is that remember the patent pool litigation that goes on back in Congress passes a law about monopolies and all that stuff back around the 1900s. It had to do with these patents that Tesla had sold to Westinghouse. And Westinghouse owned a monopoly on the whole North American power grid. And GE couldn't get in there. So since they couldn't get in legally, and they couldn't get in by intellectual smarts, there's always another way, and that's to go deal with the politicians. And that was how they got in there. But look, Alexander said, in every branch we can of radio and power engineering, we can trace the spark of thought back to Tesla. But really, the advances in electricity begins to become something more than just a parlor diversity with Faraday. And of course, then the wonderful work that Maxwell did. Remember when Maxwell got the inspiration to add the displacement current term so that you got conservation of charge in what today we call Ampere's law. Was it Helmholtz, or was it not Kirchhoff, but I guess it was Helmholtz, when he first saw the paper published by Maxwell. He was holding it in his hands, and he quotes those lines from Goethe's Faust. Was ein Gott, der die Zeichen schrieb? Was it a God that made these symbols be? You know, and those of you that, of course, you look at Maxwell's equation, you know, all these magical symbols that do all these wonderful things. I mean, the lights we have today, this stuff, you're seeing me, I'm seeing you, all because of Maxwell's equations, right? And Helmholtz recognized that. RF. We want to look at the experiments of Helmholtz and Hertz. Tesla, overnight, does something magical. You know, he goes to Bonn and talks to Hertz and realizes what Hertz got it. This is a toy. This is nothing. He comes up with a very clever process for increasing the average power of an RF generator by 5 orders of magnitude. One flash. Do this, and the power goes up by 5 orders of magnitude. Right? Imagine we could do that today. Just come up with some scheme, do something to circuits that we have that everybody's working with today, and our power levels go up by 5 orders of magnitude. Right? That's what Tesla did. Well, you know, I wish I had time to tell you about this guy, Marlon Loomis. He actually builds a transceiver, generates RF, transmits over 14 miles, receives it, demodulates it, detects it in 1864. It's demonstrated before Congress in 1872. Congress passes the Loomis Telegraph Act. It's signed by the president, who was Ulysses S. Grant. And there's a stock market crash. Loomis loses everything, and radio engineering stops at that point in time. It's an incredible story, absolutely true. While we were at Battelle, we repeated some of those experiments. And since then, we found out how Loomis's transmitter worked. And since then, we found out how his detector worked, and a very sensitive detector. That's another story. We'll say that for another time. Armstrong. You know about Armstrong. Of course, Armstrong gives us not only the super regenerative detector, and the super heterodyne receiver that is used, every TV set in the world uses the super heterodyne principle, but also the frequency modulation technique that we have. Armstrong, of course, was also a worshiper of Tesla back then. Tesla, of course, gives us the Niagara Falls and the names there. This is the robotics and wireless control, as well as code division multiplexing, all patented by Tesla back in 1890. Logic circuits. And this is kind of the process that you see in the radar systems. Tesla is the first guy to describe radar using RF processing. He describes it in 1900, June of 1900. which predates the patent that this guy Hewlett had filed in England, I think in 1904. Hewlett he's typically acknowledged as a father of radar, but his work was based on, again, on Tesla's work. Particle accelerators. We know the wonderful work of Sloan and Lawrence and Louis Alvarez. What they did was a continuation of the work that Tesla did. It's built exactly on Tesla's Tesla coil. Tesla creates this cavity resonator process that they subsequently used, and David Sloan was the guy that made it work. And in fact, Sloan writes a paper in Physical Review in, I think it's June of 1935, and he makes the comment that Tesla coils cannot be analyzed usefully by mathematics, which of course is bunk. It's just that they didn't have at that point in time how to handle surface wave propagation on helical structures. That didn't come until much later. Particle beam weapons. There's a guy who's fairly famous, Nikola Tesla, who unfortunately passed away about 30 years ago. But when you look at how Tesla came up with the particle beam weapons stuff that became part of the charge that President Reagan gave to the defense lab, Christophel's work again was based on Tesla. In fact, if you look at some of the papers published by Christopher's, they're word from unpublished documents on file in the Tesla Museum in Belgrade. Right? I mean, the museum's still there. Terrestrial resonances. Tesla is the first guy to actually excite terrestrial resonances, and he's got the correct frequencies. Typically, we give credit today to Winfried Schumann, W.O. Schumann, in Germany for first figuring out, you think of the Earth and the ionosphere as a concentric spherical shell, like a big capacitor. Well, if you go to a high enough frequency, what happens is that spherical cavity there begins to have resonances. And these resonances begin at about 7.5 Hertz and so forth, and they can use them for detecting high nuclear detonations high in the ionosphere because the frequencies change and so forth. But the funny thing about this is, and I pointed this out to Jim Waite just before he unfortunately passed away in 1998. Waite was probably the foremost electromagnetic wave propagation engineer, at least in our lifetime. I think he has, his citations are only second to Maxwell in terms of electromagnetics. That in fact, the Schumann resonances were accurately predicted by J.J. Thomson in 1893, who based his work on Tesla. Okay. Weather modification. Here's an area where we don't have anything, I can't tell you that anything has been experimentally verified. The other areas, we have experimental data on all of it. But Tesla hypothesized and proposed weather modification in the early 1900s. And the interesting thing about that is that John von Neumann, when he's testifying before Congress, I believe it's in 1956, von Neumann says, and this is in the collected works of von Neumann, right? Who did all the work on quantum mechanics and all that stuff. You know about von Neumann. Von Neumann said, by 1981, he realized in 1956 that weather control will be a significant part of the defense of the nation. And hasn't happened yet that I know of. Okay, all right. But I just wanted to let you know a little bit more about his background. This is probably the greatest tribute that I know of to Nikola Tesla. Can we keep the lights out here for just a second? My transparency isn't very good, but it's the best that Kinko's could come up with. There is a wonderful web page. There's a NASA web page where they have all these photographs of the day or whatever, and if you go back to about 1998. This is a composite picture, and they call it Earth at Night. And what they did was they just took a montage, a collection of photographs of the Earth that were taken from satellite. Whenever they went over and it was night, right, and they put them all together and they got this picture. But this is really, I think, the highest tribute we could give to Nikola Tesla, because every one of those lights that you see is passing through the generators, power distribution system that Tesla conceived in the late 1880s, right, and was finally implemented by the turn of the last century. The electrical power flowing from our great generators, illuminating our vast cities, dispelling the inky blackness of the night. Right. Not only that, and the telecommunications that you can't see on that picture, cohesively linking the homes and businesses of our civilization across continents, around the globe, and through the distant reaches of space. These are monuments testifying to the successful life of this little-known, but uniquely admirable scientist, inventor, engineer, futurist, citizen of the world. This picture doesn't include radio communications. It doesn't include satellite communications. It doesn't include electrical machinery. All those things are also present there, and these things all testify to great tribute to Tesla. I remember back in November of 1965 when they had the big blackout in the Northeast. I was a grad student at the time at Tufts University, and driving home, all of a sudden couldn't hear WBZ in Boston anymore. In came WLS out of Chicago. I was like, what's going on here? What happened to all these Coast radio stations? And when I got home, there was no electrical power, the lights are out. It was about a year or two later, I think this is in Life magazine, there was a congressional inquiry to find out what was going on, and they called up Highland Rickover, who was the father of the nuclear navy. And I don't remember too much else, but Rickover, testifying before Congress in the late 1960s about civilization's infrastructure, made the comment that electrical power is the last system that I want to see go. He says, take the water, take the sewage, take anything else. He says, but leave us electrical power till the end. Right? So, anyway, all right. This was kind of interesting. This is on the Tesla webpage. It's www.teslasociety.com, I believe. Right? This is from the New York Times last August. It's on there probably someplace. August 15th, was it? Yeah, August 15th. Right? So this is the day. This was published the following day. This is sunset over Manhattan. Okay. A friend of mine made the comment, 4 million people the next morning. 4 million people. Not one cup of coffee. So here's what the vice president of the AIEE said the night they gave Tesla the highest award that the IEEE, back then the AIEE, had to give. And this guy's name was Dr. Bernard Behrend. Behrend was a very famous consultant. And he wrote this. And it was prophetic because it happened. Right? Were we to seize and to eliminate from our industrial world the results of Mr. Tesla's work, the wheels of industry would cease to turn, our electric cars and trains would stop, our towns would be dark. Now, he's writing this May 18th, 1917. Our mills would be dead and idle. It's particularly pleasing to me to pay tribute to the inventor of the motor and the system which have made possible the electrical transmission of energy. Mr. Tesla, we beg you to cherish this medal as a symbol of our gratitude. That was written by the author of the first English engineering text on AC power system and the induction motor. In fact, when I was down at Clemson University in the archives down there, which is where Behrend's collected papers are, I came across this photograph of Tesla. And on it was written in Tesla's bold handwriting, my dear friend, Bernard Behrend, you understand me better than anyone else. Right? Because Behrend had written that engineering text about the Tesla system. Okay. This is where we want to go tonight, though. I said all that stuff so I could get to here. This is Tesla's Colorado Springs laboratory, where some magic is about to happen. This is 1899. He's already got Niagara Falls up and going. Westinghouse is making money. Tesla's got, his pockets are filled with bags full of gold. In fact, Tesla wrote an article in 1936 it's in 1934 in Scientific American. And there's a sequel to it, I think, one is in March, the sequel's in April 1934. And Tesla makes the comment that, he says, there's no wall so high that a donkey loaded with gold can't jump over it. If you only have enough money, you can get over it. Okay. Well, at this point, Tesla's got the money. Right? And he already has the idea for a power distribution system that will work without wires. Right? Now, nobody's ever gotten a system to work since then. I wish I had time to go into great depth about what he had to say, but when he received that medal in 1917, when they were giving him all those honors, he made the comment that there was no doubt in his mind that this system would work and would be used. And he saw it being used within a few decades. Right? That's 1917. And a lot of years have he says, I have documented proof that the system works. What's happened? How did our engineering profession miss this? Well, anyway, he builds this 50 by 50 building out there. That's Pikes Peak off in the background. You can go to this very spot today. Notice it's kind of on a hill, and it's at the intersection of Kiowa and Foot Streets in Colorado Springs. And if you look back looking that way, you'll see Pikes Peak. If you look this way, you'll see Prospect Lake. There's a park nearby there. And if you look over this way, you'll see the printer's home, which is a very famous printer's home with a big clock up on there, with a clock stuck at 8 o'clock, with the arms engraved at 8 o'clock. It was at 8 o'clock because the printers were the first union to be able to get an 8-hour workday. And that was the big deal. Anyway, the printer's home for retired printers was there. But this is the laboratory that he builds. And we'd like to take a closer look at this tonight. Here's another view of it. He's written something on the side of this picture. And what he has written is experimental station, fully developed. You turn it sideways so you can read it. Experimental station, fully developed. Activity. Now you got to realize that the terms that we use today, he didn't have back then. He couldn't say, I will now use a laser and do this. Because the word laser didn't exist back then. I'm not sure. Laser may be the wrong term, but you understand what I'm trying to say. So when he says activity, parenthetically says, well, power delivery. 100,000 horsepower. All right, 100,000 horsepower. All right. How many watts is that? 100,000 horsepower. Well, what's horsepower? Right. Horsepower is 746 watts. 746 times 100,000. Right? It's about 75 megawatts or so. Yeah. So how did he 75 megawatts? How's he doing that? Now, you got to realize that he was tied in by 1,000-volt mains to the electrical power distribution system there in Colorado Springs. And the actual average power he's running is about 150 kilowatts. And that's how much power that he actually is running there. Let's see, what he was saying. This is looking west at Pikes Peak. Cheyenne Mountain is nearby. By the way, that photograph was taken by Nixon Alley, who was a fairly famous, brought his own photographer out there. And both of this photograph and the previous one were taken by moonlight as a time-lapse photography. You can see the light is on in this office in the side here. Well, you've all seen this picture before. It's actually a double exposure. There's several things to notice in this picture that are of significance. One of them is that there is a fireball in here. It's not clear in this Xerox copy that I've got here. But in Belgrade, these are all glass plates. And in Belgrade, when you hold the plate up, you can look at it, you can clearly see there's a fireball there about the size of a basketball. All right, and it's located right over here. It's right at this point, right between these two studs. So if you get a chance to look at his diagram or Randy's pictures, just go out with the two studs to the wall and follow it. You can see it's right in here. It's a whole lot clearer if you've got a good first-generation photo of this thing. A couple of things to notice on this. Note the what appear to be RF chokes back here. These two things on the wall. There's actually some wire that comes up and goes around and comes around and does some stuff in another place. you kind of wonder what's going on down here. It's got a whole bunch of stuff in there. If you're going to rebuild this, you'd like to be able to replicate the experiment. Right? I can tell you this, that we've published a lot of papers on Tesla's work over the past 20 years or so. Okay? I don't know, about 60 papers or so. What we have found is that every time you do what Tesla said he did, you create those conditions, you get the results that he said he got, right? And, there's this problem of creating ball lightning. And what we found was that if you arrange your apparatus the way he describes it in his diary, you will generate ball lightning. We'll show you some pictures of it in a little while. Something else that's interesting. Notice, by the way, this fence is 8 feet tall. This is the secondary of a coil. Primary is laying on the ground, and it's, let's see, he's got two bundles of 37 each of number 9 copper wires. They've got a lot of copper. That's his primary, twice around there. He's got, I think it's 20 turns on his secondary here. And then that feeds this other thing here. Those of you that are ham radio operators can tell you this is a rubber ducky. You'll understand that in a few minutes. Alex will know rubber duckies for 2-meter handhelds and so forth. I don't know what they use on 2-meter. This is a rubber ducky that works at 85 kilohertz. And you'll see how in just a minute. Something else that's of interest, though, is this right on the top of the secondary. He's got this extra turn. And what's of interest in this picture is the fact that there is no corona on that turn. I realize here that we're talking about some high voltages here. He's running only about 12 megavolts in this apparatus. Okay? He talks about getting to much higher voltages than that. The 12 megavolts is a substantial amount. Sparks, by the way, he always considered as wasted energy. He says, I merely do it for your entertainment. Okay. One other picture. This is of interest because this is the extra coil, and what he has put on here as a caption is normally excited. Okay? So that's normal. Well, okay. How do we engineer this thing? How do we tune it up? How do we build this and make it go? This is also of interest to us because in the article that he writes when he comes back, a close friend of his was the editor of Century magazine, sort of like the Saturday Evening Post or something back in 1900. And when he comes back, he writes this very lengthy article. He was asked to write an article to explain what he was doing. And if you've ever read the article, and you realize he talks about everything under the sun but what he was doing. But in this article, he describes this, and this is the comment. This is puzzling. He says, all right, view of interior, chiefly showing the condensers. These are condensers. He has these saltwater bottles. He had to build his own capacitors, right? And what they actually did was they went out and got these champagne bottles, dumped out all the champagne, and took the bottles and made capacitors. So these things are, each of these cups are filled with salt water, and these bottles to be able to make his own capacitor. Well, it's not clear they just dumped out the champagne, but I mean, This is the 8-foot high fence. This is a rotary coil, so he can tune his inductance. This is his Westinghouse power transformer. It's actually rated at 50 kVA. And he says, oh, the oil in this is good. He says, I can run it to a whole lot more than that. And he actually takes it up to 150 kW. And he says, oh, I can run it higher than that. That's all they can give me at all they can generate at the Colorado Springs powerhouse. All right, so you've got capacitors and coils, and we're going to talk about resonating the Earth, and how does this happen? The explanation is, his patents provide you with numbers. Right? So it isn't just like he's writing a lot of patents are pure nonsense, you know that. read the patent, you think, this is how it works. I mean, somebody back, I remember when I was filing some patents back in the early 80s, a patent had just gotten through on a perpetual motion machine. And some idiot gets a patent on that kind of stuff. Now what happens is anybody with a legitimate patent after that, you've got to move heaven and earth to convince them because they'll make that mistake again. And but he provides numbers, and he tells you, let me turn it on. The apparatus is documented. So all right, so you got to put this together. You got to build one yourself. It isn't enough just to know the values of the circuit. You got to know how to tune it. And what was he doing? So there's a proverb. Electrical engineering and physics. These are sacred professions, as is astronomy. And Solomon once said, it's the glory of God to conceal a thing, but the honor of kings to search out a matter. And we're kind of in that position even today. Tesla felt no compulsion to disclose anything more than what he felt was necessary. And in fact, in 1916, he's talking with his attorney, and he makes the comment, and it's published in one of the books available today. He says, well, others that have come after me have had troubles trying to replicate what I've done. And he said, it's not my fault. He says, I've published all this stuff. It's not my fault that other people can't do this. And he says, anybody with no more training and understanding than I have can do it from what I told them. Well, I think the 20th century is probably pretty good witness to the fact that there haven't been many people that have had no more than what he says is no more than my training to be able to understand this. All right. I haven't gotten to the start yet. I'll do the best I can. I had to give you that background so that you know what's going on. Let's go back to Hertz. All right. Hertz, 1887 is given by von Helmholtz, who's his advisor. Von Helmholtz is in Berlin. Hertz takes the position, I think it was there. Yeah, and he goes over there to write his dissertation. Right. And he performs marvelous experiments. How does his equipment work? What Hertz, I don't have the pictures with me, but the pictures are available of replications from his 1887, 1888 papers. Right? And it's essentially like this. He's got a buzzer that is going to give you a DIVT here, which is going to give you DDT, and that's going to give us a stepped up voltage, E2 equals NV1, and we can get the voltage here. So we're going to get a lot of volts here. He's got these things, and it's about 3 meters is the length of this thing, capacitively loaded at the ends, with a spark gap here. So what happens is, when the voltage appears here and is building up, reaches a point, of course it's charging up these capacitors, it reaches a point here. How did he build a signal generator? You guys were in the lab. I used to tell this to the students when we were here before, because we had heat-kit signal generators. You guys were in the lab, you had a heat-kit signal generator, it tunes the frequency one. How did Hertz do it back in 1887? When the heat-kit there you could deal with. I don't know what you did. Hewlett Packard, I think, is what I saw in the other. Boy, IT has come a long way from heat-kits to Hewlett Packards. Your labs are beautiful. Okay? I think there are a lot of places that would envy. Anyway, what happens, of course, is these capacitors charge up. Think of them as in a quasi, it's happening at 15 kilohertz rate or so. I mean, or less, because it depends on the buzzer. And they charge up until we hit breakdown here. When we hit breakdown, we get RPM. It's like somebody threw a switch. And now the charges on this will realign. And as they realign and slosh back and forth, what happens is we get an LC discharge. And since the physical size of the circuit is on the order of the same size as the oscillation wavelength, we begin to have radiation, because the thing is an efficient radiator. Let's see. I didn't write down the frequencies. Well, correspond to about 3 meters. Actually, it's a little bit less than that. Peak powers that, you always hear about the peak power that Hertz was running. I think it's like 5 or 10 kilowatts. His average power was about 500 milliwatts. All right? I told you that when Tesla went and conferred with Hertz, he came away thinking, this guy Hertz doesn't understand. By the way, the news media when Hertz did these experiments, went to Hertz and said, yeah, Professor Hertz, will this make possible wireless communications? What do you suppose Hertz said? No, I don't think so. This is 1888. Hertz was right, because this wouldn't make possible wireless communications. What made possible wireless communications was the apparatus that Tesla disclosed and patented a couple of years later. Right? And what Tesla found was a way to, look, the amount of energy that's radiated here is a half CV squared. All right, what do we got? We've got, that's the energy now. We've got to see this picofarads. How many picofarads? Probably about 50 or 100 picofarads. And the voltage, as I said, was probably about, be generous, say 10 kV. From that, you can figure out how many joules, and how many times per second did he do this. And he did it 1,000 times per second at 5 kV. With 50 picofarads, he gets an average power of 500 milliwatts. Tesla realized there's a flaw in Hertz's apparatus. And here's kind of the family tree for microwave engineering. Or we could say radio engineering, or cavity resonators, or particle accelerators, what have you. Here's Lloyd Kelvin formulating the conservation of energy. And what Hertz did was to take those capacitor plates and open them up. And for the inductance, he just used the inductance of the linear wires that he's got to get the highest frequency he had. He's got a distributed tank circuit. What Tesla said is, you know, if I use coupled coils, and I have a small C here with a large L, and a little L here with a big C, then my half CV squared, I can make orders of magnitude. Tesla went from picofarads to microfarads in 6 orders of magnitude. So his power level rises by a factor of 10 to the 5th. That's, I say 1891. It's actually 1891-92. He's doing that, and that's when he went to see Hertz. When he comes back, I said 1898 here. It turns out that it's actually about 1895 that he realizes that he can take this lumped coil that he was using and begin to use the distributed coil. Okay? And what happens is this guy turns into a quarter wave resonator. Right? When he goes to Colorado Springs, he's got an apparatus that looks like this. Realize that these are the power mains, and he's actually using a dual symmetrical center tap system here, so that he's, you know, he can hit it on both half cycles, and he's able to get his switching speeds up to very high frequencies. His secondary, which was that big fence, is nothing more than a local master oscillator to excite this quarter wave distributed resonator that he's got over here. Now, the reason why he uses quarter wave is because you remember that Vmax is S times Vn. I run with a very high SWR, quarter wave length long. Whatever the voltage is here, I can step it up by the SWR. I mean, I've got a lever here that can take a few 100,000 volts and easily step it up to 10 megavolts or so. And every successful Tesla coil that you'll see today does that. All right? Now, I'll say more about that in a little while. David Sloan, in 1935, and this is the article that's in Physical Review. And that's a good article. Everybody should read that one. He's in need of high voltage, megavolt or so, to drive an X-ray tube. And so what he does is he takes this helical resonator. He doesn't need this apparatus anymore. He actually uses vacuum tube transmitter at 7 megahertz. He was a ham radio operator, and he built this 10 kilowatts transmitter for the 40-meter ham band. Of course, it's illegal then, legal today, but anyway, your grandson story about this thing. But he put the helix inside of this coaxial cavity, evacuated it, and then shot electrons in the side here and was able to generate X-rays up here using the voltage. And they used it for medical purposes out at Berkeley at what has later come to be the Lawrence laboratory there at Berkeley. Cavity resonators were first introduced into radio by W.W. Hanson. In fact, Ginsburg, who wrote the book on microwave, the McGraw-Hill book on microwave measurements, has a nice picture of Hanson and attributes to Hanson the title of father of modern microwave engineering. out at Stanford. What Hanson did, of course, look, you got to realize that the solution of the wave equation for a bounded conducting box was actually worked out by Lord Rayleigh in, I think, 1896 or so. It forms the framework. Was it 6 or 8 years later? What's his name? Max Planck uses it. Remember the ultraviolet catastrophe and all that stuff? Uses that solution to begin to formulate the Planck-like body law, right? With the thermal radiation from the walls of the cavity. But nobody had used it in radio as a tuned circuit until Hanson, right? And what Hanson does is he takes Sloan with a helix inside the can. He says, I want to go to higher frequencies. So I'll unwind the helix. So now what you got is like a coaxial cavity resonator. And that's what Hanson introduces in 1938. And then later on, he says, I want to go to higher frequencies. He pulls the center conductor out, and he's back to this loop-coupled cavity resonator. It excites the fields inside of the structure. Let's see. I should mention also that this structure is subsequently used by Louis Alvarez, who was able to make the first proton LINAC, linear accelerator, using this. But look, all the way back. Where does it go? It comes back to here. This is the first distributed high voltage structure. First RF high power oscillator is built by Tesla. 5 orders of magnitude when we pass from Hertz to Tesla. No energy wasted in the form of radiation. That was another thing that Tesla wanted. Tesla in 1916, when he was talking with his attorney, yeah, I'm going to wear you guys out. I don't know what else to do. Let's see. When will I get to talking an hour? Just about now. Let's see. Tesla in 1916 made the comment that every wireless message that has ever been transmitted to any distance by this apparatus. There is no other way. There is no other system that is used. And the same can be done today. They're still using that same system of tuned circuits. Okay, so I got through the introduction file. Tell you what we're going to do. We're going to take a break so that those of you that you've heard enough and you've been very, very courteous as an audience, and you wanna go home. We'll let you go, and we'll let everybody take a break. And what I'll do is when we come back, I want to tell you about this stuff. These are fireballs, and you got to realize that we've taken these discharges about 22 feet or so. These are about the size of ping pong balls. And they actually come spraying out. When I was out at Colorado Springs at a symposium on there once, somebody said, the way Tesla describes these things, they sound like, it sounds like they're almost like bubbles coming off the Lawrence Wells bubbles machine. How come nobody sees these things? And so my brother and I took the challenge, and we said, well, we've got to find out how he did it. And what's happening is these things actually come bubbling out, and of course we've got discharges going on, and what happens is the discharge follows the fireballs. That's an important key, especially if you want to do directed discharges. Right? And we'll tell you about this when we come back. Why don't we take a break for... You'll all be back here by 4:00. All right? And anybody wants to go, you can go.